Hi everyone, it's Ben Jordan here with the OnTrack Whiteboard video series. Welcome back. And today I want to talk about RF and microwave. I like to use the lambda there. Hope you don't mind the pun. RF and microwave PCB design. This is actually part one of several episodes I'm going to be doing over the coming months, talking in general about all the ins and outs of designing boards at radio frequencies and for microwave applications, because a lot of people are kind of intimidated by the idea of doing microwave PCB design and aren't really sure where to start. And I was that guy, you know. I wanted to learn about it. I was a little bit afraid to try it, and I started doing some research and realized, you know what, with the right guidance, any good PCB designer can do RF and microwave PCB design. So that's what we're talking about. And today, I want to talk about a few of the absolute basic fundamental things to start with. And some of those things are around materials. Some of those things are around the actual physics of RF and microwave propagation, but we'll go into more depth in the coming episodes. So let's begin. I've got a little example here of a piece of, section of PCB substrate, and you'll note I've drawn it with some copper on the bottom there. That's effectively a copper plane. That's a reference plane, and a trace, a microstrip line trace on the top. And this is pretty typical of any PCB trace. And they're connected to each other through the substrate. The substrate is a combination of usually epoxy or some kind of thermosetting plastic material, reinforced with glass fibers, typically, almost always. Some older or cheaper boards use paper, like paper phenolic resin for FR1, and for the most times recently, FR4 is the most common, cheaply available material, and you can actually do some RF design on a typical FR4 PCB, but you need to know what's going on. So first, let's talk about conductors. At the frequencies, well, first of all, let me actually say, what is RF? Really, RF, or radio frequency, is anything like 300 kilohertz or above, technically. And you can go on the FCC website, for example, or if you're in another country, there'll be a government website where they have information about laws that regulate the use of what we call the spectrum, the radio frequency spectrum. And but really, as far as RF and PCB goes, we're talking anything that's intentionally processing analog signals or amplifying or carrying analog signals from an antenna or to an antenna, or at those frequencies kind of in the megahertz and above. Microwaves is when we get up around 1.5 gigahertz and above. And so at those frequencies, a few things behave differently. So first of all, let's talk about the most important thing to know when you're dealing with different RF or microwave frequencies, and this is wavelength. So if we're dealing with signals that propagate through the air from an antenna, for example, we're dealing with lambda 0. This is the wavelength at the speed of radio frequency signal propagating through air or vacuum. Air is close to vacuum. So it's basically the speed of light over the frequency. So basic stuff, right? And anyone who's studied or does ham radio would know, like, an easy way to calculate that is to say speed of light is 3 times 10 to the 8 meters per second, but if you call it 300, you can put F in megahertz. So if I have a 2.4 gigahertz, which is the Wi-Fi or Bluetooth sort of range, 2.4 gigahertz signal, I'd say 300 over 2400, and the wavelength in air or vacuum of a signal at that frequency is approximately 16.67 centimeters, right? So you're dealing with, this is one full wave, and half wave and a quarter wave. And in future episodes, we're going to talk a lot more about the significance of those multiples of a quarter wavelength are very important in the PCB design. So 16.67 centimeters. Now, if you're in a PCB, it's a bit different, because in a PCB, we have this dielectric. And the dielectric is made up of all sorts of different molecules in a glassy kind of plastic. And of course, then we have the e-glass fibers, which are the reinforcement. And if we, this is an oversimplification, but it's just to help understand. We have all these domains of the chemical which are insulators. However, those insulators, like any material, they're made up of protons, neutrons, electrons, in some bigger structure. And so they can hold an electric charge. And they can't conduct, but they can hold charges in different random orientations. And when you put a voltage between two conductors, so the trace and the reference plane is 0, and we have a pulse voltage on the trace, so 3.3 volts. What we're doing, where that voltage exists, we're forcing the molecules in the insulator to align their charge domains, because like charges repel and dissimilar charges attract. And so having a voltage applied across a dielectric creates these charge domains to orient themselves, and that's kind of a mechanical or that's an actual physical phenomena, and that gives rise to capacitance and what we call displacement current. And so as a signal travels down this trace, and this is for any kind of digital signaling as well, not just RF and microwave, but also pulses in a digital system, as the voltage travels down at a finite speed down this trace, it has to charge those domains in the insulator between the trace and the reference plane. Okay, so that takes time. Unlike a vacuum, that takes time and effort, and so that time and effort to orient these charges gives rise to a different propagation velocity in the material of the substrate. So in a PCB or any other material like a coaxial cable or some other kind of cable or any kind of insulator, we have what's called an effective dielectric constant, or dK, as you may know it. And this is typically an attribute on a PCB material data sheet. dK, it's also sometimes called, and the proper engineering term is epsilon R. It's the relative permittivity of the material, and that gives rise to an epsilon effective, which is recognizing that this material is not just one solid homogeneous material, but a mixture of materials, resin and glass, and we kind of treat it like a homogeneous thing, and it has an effective dielectric constant. So let's say typical FR4 effective dielectric constant, dK for FR4, dK would be approximately 4.2. And then what's the wavelength of a 2.4 gigahertz signal on an FR4 PCB with an effective dielectric constant? Then our formula for wavelength changes, and we have what's called the guide wavelength, lambda sub g, and that is the speed of light, simply put, speed of light over frequency times the square root of the epsilon, right? This is an oversimplification, and in coming episodes we'll get into more detail, not to dive too much into the maths, but we'll explain it a little bit and then use some calculators, because that's a lot faster, okay? So anyway, in this case we'd have 3 times 10 to the 8 over 2.4 gig square root 4.2, and that gives us an approximate wavelength in a PCB of about 6.1 centimeters. Right? So the frequency, number one parameter you need to know when you get started with PCB design at microwave and RF frequencies is obviously what's the frequency you're operating at. That tells you what's one wavelength, and from there we want to derive all our other work based on a wavelength or a fraction of a wavelength, typically a quarter wavelength. So when is your PCB design going to be an RF PCB design? It's when the length of your interconnects becomes some significant multiple of this, or fraction of this, I should say. And the general accepted industry standard, if any of you are electrical engineers, many of you are, you'll remember this from your transmission lines class and fields and waves. The general rule is when your length of an interconnect on a PCB is going to be greater than or equal to, less than or equal to 1/20th of the guide wavelength. If you're dealing with lengths around 1/20th or shorter, those no, it's greater, sorry. At that point, you're dealing with an RF or microwave design, because the length of the traces and features you're dealing with at that point have a profound impact on how the circuit actually operates. If you're going much beyond that, then or if you're much smaller than a wavelength, so if your frequency is much lower than the characteristic length of traces on the board, then the length of the traces is so tiny compared to a wavelength that they can be treated as lumped elements. Okay, so let's talk about, so we've talked about insulation material, guide wavelength, all of that. Let's talk about conductors a tiny bit. Here I have a cross-sectional view I've drawn. If you get a section of a small PCB trace and you look at it under a microscope and it's polished, you'll see the surface of typical PCB copper is very rough. It's actually intentionally made this way. They take the copper and it comes off a drum, and one side of it's smooth and the other side is rough. It's called electrodeposited copper because of the plating bath that's used to get copper out of solution onto a drum. And they make the foil out of that, and they want it rough on at least one side because that helps it adhere. This tooth, this is called the tooth, and that helps it adhere, like grab into the insulation material during the lamination cycles. But that causes a problem too, because at very high frequencies, particularly microwave frequencies, this thing called the skin effect, and again we'll talk about it more in a future episode, causes most of the signal to travel just in the surface, just in the extremely thin surface of the copper, and that effectively increases, that surface roughness effectively increases the length of the transmission line significantly and leads to pretty significant losses. And so we may decide, doing RF PCB design, if you're going very high frequencies, like above 10 gigahertz, you probably are getting into a realm where you start to need to use different types of copper, and you need to specify you want rolled annealed instead of electrodeposited, or you may even have a specific manufacturer part number for the copper you want to use. For under 10 gig, if you're not going too far and you can design around the losses that you'll get, you can use standard FR4 and standard electrodeposited copper. You just need to know what to do. And finally, in this introductory episode, the last thing I want to talk about, I mentioned this whole concept of wavelength and why it's important. Just one other thing that's going to lead to what we discuss in the future is this notion that people think of current and voltage, and you think of it in a traditional circuit analysis way. That is, we have electrical conductors and current goes in loops around the conductors. And in the PCB design profession, particularly within the last 5 years, we've had a lot of really good training from industry experts like Dan Beaker, Rick Hartley, Lee Ritchie, Eric Bogerson. You know, you've all heard of these guys, and they're fantastic. And what they've been teaching us is what we really need to think about is the energy. And the energy is traveling, the energy of a signal is traveling in the space in the form of the fields and waves. And this, for anyone who's studied electrical engineering, you know this. It's from your fields and waves classes in 3rd and 4th year engineering school. But it's important to remember why and how that actually happens. We are in the electronics industry because we are still dealing with electrons, and they're charged particles. Electrons are negatively charged, and when an electron moves away from a nucleus of its parent atom, the atom itself, the nucleus, is positively charged because of the protons in it. So in conductors, electrons can move around freely and be shared and jump around, and this is why metals form nice crystal lattices, is because they're sharing electrons, and the electrons are mobile and they move around. And magnetic metals like iron, the electrons can all move in sync together and give rise to a magnetic field. And that's how permanent magnets work, for example. So in any conductor, we can actually place a voltage source and have the electrons at one time instant all go away from the middle. So we have a net positive charge in the middle of the conductor and negative at the extremities. And this would look, if we could graph the voltage over the distance of this conductor, we'd see this kind of wave form. This would be a positive half wave, for example, of a sine wave on this conductor, where it's 0 in the middle, and we have, sorry, that's a sine wave there. We're just looking at it phase shifted. We have negative at the extremities, positive in the middle, and 0, like net 0 charge somewhere a quarter of a wavelength in from each end. Now, at another time instant, all the electrons, it's just think of it, it's like a trough, and there's water, and there's a wave of the water, and at one moment there's more water in the middle, and at the next it's down in the middle and bigger at the edge, and it can go back and forth like this, right? So here we have a positive goes to a trough and a peak at each side. So we're positive over here, and in the middle we're at a negative. And this, when we have this is one full wavelength, right? That's one wavelength, if I can draw that upside down, on that piece of conductor. And when we start vibrating this around and around, this gives rise to propagation. And most people have heard of the term dipole. A dipole is a piece of metal, effectively, or two pieces of metal, like this, connected to an oscillating voltage source. And this whole thing is one half wavelength apart. So at one instant, this voltage source pushes all the charge down to one end, and it's very negative here and very positive here, and then it reverses and pushes all the charge back up here, so it's very negative here and then very positive here, and that gives rise to propagation away from that. And this is how antennas are built. This is how antennas work. And so here I've got RF drawn like antennas, and we'll talk about PCB antennas in our final episode because that's the most complex sort of thing to get to. but we'll just give a basic introduction of what kinds of antennas are out there. And also these metal structures that are multiples of 1/4 wavelength are very useful in designing the actual board. So we'll go into some detail in episode maybe 3 about what we can do to design an RF circuit using just pieces of copper on the board, which is pretty cool. I think that's pretty cool. So anyway, that's all I've got time. I've probably spent way too much time today, but I hope you find that useful. If you really like this and you want to pay attention to the series and know when the next edition or when the next episode's coming up, please subscribe. If you like it, give us a thumbs up and share it. Please feel free to share with your colleagues and friends in the industry, and comment below, and I'll do my best to answer any questions. And thanks very much for watching. This is the OnTrack Whiteboard series.